Can you hear me? Okay, great. So just for the video to pick up, we're now basically talking about lecture notes number 4, which is essentially talking about small signal design, or really how we're going to do small signal design, but hopefully in a much more productive way than just brute force sweeping things in HSpice. So as we were mentioning a second ago, as we said, Spice is really kind of good for verification. But we really would like to have some kind of hand model to allow us to actually come up with a reasonable design procedure. But of course, the problem there is that all the hand models we talked about basically were way off for any kind of modern transistor. Okay? So the question we're really going to be addressing today is exactly this challenge of how can we come up with an accurate and reasonable hand design methodology when any sort of typical model that we've come up with, which would be analytically trying to capture the transistor behavior, probably is not going to be very accurate. Okay, so in order to do that, what we're going to see is that we're going to come up with a methodology where we're basically going to use Spice as a lookup table. But to kind of motivate how that would really work, it's useful to point out sort of one important thing, right? So if you're the layout designer, in other words, at the end of the day, you're putting together the actual mask set for what's going to be fabricated, then indeed the parameter you care about in terms of at least the transistors is like just the dimensions, right? The width and the length. That's kind of all you really need to know about. But typically as a circuit designer, the width and the length in and of themselves are not really typically what you care about, right? What you actually care about is some circuit level parameters. So as an example, you care about how much gain you're going to get. You care about how much bandwidth your circuit is supposed to have. You care about how much power it's going to dissipate. You care about, for example, how much voltage swing you can get out of an amplifier, right? But all of those are not really directly, well, I shouldn't say related, but they're not really, it's not that the width and length intrinsically tell you something about those parameters. It's usually that the width and length are something you'd sort of calculate or decide based upon these other specifications that you're interested in. In fact, even if you looked at sort of inside of these specifications, you looked at, what are the underlying device parameters that you really cared about, I would claim that you don't really care about width and length. You'd actually care about, again, some other metrics. So as an example, with gain, you'd really care about the transconductance GM and the output resistance RO, right? Similarly with bandwidth, you'd care about GM and the capacitors, right? For power, you care about obviously what's the voltage and what's the current, right? So again, really the point here is that width and length are not really exactly the parameters of interest to you. It's usually other parameters that would then basically be used to figure out what the width and length should be that are much easier for you to think about from a circuit design standpoint. Okay? So as I mentioned a second ago, that's really kind of the key intuition we're going to use to come up with what I believe is actually a very straightforward of doing design methodologies for a lot of the analog circuits that you're going to be interested in. Okay? So in particular, what we're going to do is we're going to figure out what many of the circuit parameters have to be based upon the specifications that you're given, without looking at BSIM whatsoever, in other words, without doing any SPICE simulations at all. And then the only way we're going to actually use SPICE is just as a lookup table to map from what these circuit level parameters you actually care about are into what the actual device dimensions really need to be. Okay? And we'll see that once we've done this, this is actually a pretty powerful methodology because it really lets you very, very quickly do designs in a very productive way. Okay? So in order to do that, of course, we need to look a little bit at just, what is the small signal model that we're going to be dealing with? Because as you saw, most of the parameters in that previous example were small signal themselves. But kind of the good news here is that from the standpoint of a small signal model, it pretty much doesn't really matter what the device itself is, long channel, short channel, gate leakage, no gate leakage, etc. At the end of the day, the small signal model is always the same, right? In the sense that it's always just set by the derivatives of, for example, if you're interested in the so-called GM, it's always going to be set by essentially the derivative of the drain current as divided by the derivative, the derivative of the drain current with respect to the gate to source voltage, right? So in other words, all our small signal model is always really going to be is something that looks like this. It's always going to have a GM times a VGS, a GMB times a VBS, a GDS times a VDS, and so on and so forth. But the only question, of course, is just what are these numbers in the front? What are those actual derivatives, right? That's really the only place where a specific link to a given device technology comes into the picture, right? Because otherwise, the small signal model is always just this same small signal model. In other words, it's just a pile of derivatives. Okay? So as I was mentioning before, what we're really going to do is come up with a design-driven methodology to really figure out what all of those essentially derivatives actually are. Okay? And not only that, we'll actually show sort of how you could calculate what values you want them to take on. And then once you know that, use, again, SPICE as a lookup table to actually then go and size the device itself. Okay? So in order to do that, we do need to spend a little bit of time just looking at sort of, what actually sets the device small signal parameters. Or really, to say it in a slightly more accurate way, to kind of give us some intuition as to what the relationship between the small signal parameters are and what the actual design variables we are going to be using. Okay? So to do that, I'm going to sort of break this up into two pieces. First, we'll talk about sort of transconductance. I'll then introduce this, what I'll basically design parameter that I'll call V star, and I'll explain what that is shortly. And then we'll move on to actually talk about the output resistance. And kind of throughout this, I'll give you a couple of examples of how we really use this in a design-driven context, so that you'll see that, I'm not just arbitrarily picking these sort of design parameters and, waving my hands. They'll actually be very useful for us to actually do real designs. Okay? So before I sort of dive into that, any questions so far? Or? Okay, great. So if there's no questions, then let's again start out by looking at the transconductance, because we'll see that actually most of our design procedure is really going to be driven by understanding transconductance. Okay? So here I'm just sort of showing you, let's say, a so-called fairly classic form for what the GM actually is as a function of the bias current for a long channel or really square law device. Okay? I'm assuming many of you guys, or at least I should say actually all of you guys, have seen this several times before. But in particular, I want you to pay attention to what I'm boxing down over here on the bottom. Okay? So all I did was I took the, sort of a couple of the standard equations that you may have seen for either the drain current or the GM, and I just massaged them a little bit to get them into this particular form here. Okay? So this particular form basically says that the transconductance, or the GM, is just equal to 2 IDS, or 2 times the drain current, divided by VGS minus VT. Okay? And oftentimes when we talk about VGS minus VT, we sort of refer to that as an overdrive or VDSAT. Those are all kind of equivalent names for the same thing. Okay? So as you'll see in 1 second, we're actually going to use something that looks very much like this form throughout the entire class, but we're going to use it for devices that are by absolutely no means square law. Okay? So we're going to have to make a small tweak, so to speak, to make that work. But keep this form in mind, because indeed it will be very, very useful for us. Okay? Now, hopefully there's one sort of trade-off here that should be very, very obvious, even just from this form already. So from a design standpoint, what are sort of the degrees of freedom you would really have, or how would you sort of change something about the transistor, and what would this relationship between GM and ID and VOD already tell you about that? Okay, so you actually were slightly more sophisticated. So what you said is you can have high transconductance but low input swing. So more specifically, how did you sort of link those two things together? You're right, by the way, but how did you link those two things together?
Because, as VOD approaches zero, GM approaches infinity, but at the same time, if your input percentage sort of drops the transistor into subthreshold behavior, then everything screws up.
Okay, great. So you said a couple of things that were very important there, and just to sort of recap for the camera. So the first thing you said was that, hey, look, if I change this VOD parameter, and in particular if I decrease it, I can make that GM kind of, at least from this equation, it looks like increase arbitrarily for the same bias current, right? So in other words, if I'm thinking from a sort of power efficiency standpoint, seems pretty clear that I'd like to use as low an overdrive as I could in order to get the maximum GM per unit bias current, right? That trade-off is indeed hopefully obvious and is one of the strongest ones that we'll be talking about kind of throughout the class. Okay? That's certainly true. But on the other hand, you may not actually be able to reduce that overdrive kind of arbitrarily, right? So the particular effect that you mentioned was that, for example, I may enter the subthreshold region. We'll come back to that in actually 1 second. You also mentioned that if my overdrive is too small and my signal is really big, that may cause some nonlinear effects. That's actually also true, although we won't spend as much time on that this time around. We'll talk more about that a little bit later on. But there's actually another there's maybe even two important things that also sort of come into this trade-off in terms of how you would choose that overdrive. What other considerations are there? And maybe somebody else besides you. So what other circuit level parameters? Okay, you said reducing the overdrive affects the performance. In what way? Okay, so you said it's going to slow down the transistor, so that's right. Right, so the smaller you make that overdrive voltage, effectively the larger capacitive parasitics you're going to get for the same bias current. Right? That is indeed true, and as you basically said, it's going to slow the devices down. We'll talk a whole lot more about that, but that basically says that now there's hopefully an immediate obvious trade-off, which is I'd like the overdrive voltage to be small to get a good transconductance for the same unit current. But if I make it too small, my parasitics will be very, very large, and I won't be able to get any speed out of the device. That's certainly one very important trade-off. We'll talk about that more.
Because if you're worried about getting more parasitics, does also affect your bandwidth?
Basically the same thing, right? So you said more parasitics means that bandwidth will be reduced. That's basically kind of what I'm getting at, is that intrinsically the bandwidth you can get out of the device will go down as you decrease that overdrive. Yes? In terms of power. Okay, so what about the power? Okay, so there's two things that you said there. So one was that if you reduce that overdrive, then indeed you'll get more GM for the same unit bias current. That's true. That's kind of a good thing. The other thing which you mentioned a little bit about was swing. So maybe I'm going to bug somebody else about swing. How does this overdrive, or more particularly this VDSAT, influence the swing you can typically get out of an amplifier? And by swing, I mean the voltage swing. Yeah?
For square law term, I thought it was the minimum voltage that you have to have for a VDS to be in saturation.
Yeah, exactly. So what you said was that typically that VDSAT was kind of like the minimum voltage you need in order to make sure the device was still in saturation, right? So if we looked at, let's say, a simple amplifier, and let me just even abstract away the load as just being a current source, just have an NMOS device with, let's say, an input there and an output over here, right? That VDSAT would basically say, what's the minimum drain to source voltage you can apply across that transistor? And make sure it basically stays in the quote-unquote high gain region, right, in the saturated region. And so indeed, the smaller you make that VDSAT, the closer you could shove the output to ground, and therefore the larger swing you would get, right? And of course, as I hope you guys all know as well, there's a similar VDSAT that would really be in that physical current source. So again, if you decrease that VDSAT on both sides, the actual swing you could get at the output would go up. Okay? Does this make sense to everybody? Or? So by the way, that would tend to imply that you'd like to have a small VDSAT, or equivalently a small VOD. Okay? So by the way, keep all these sort of ideas in mind, because what I'm going to do in 1 second is introduce a slightly different parameter that I claim will actually be much more useful, because it'll work no matter what the device model is. But exactly all these trade-offs we've been talking about are the sort of, at least by intuition, the same trade-offs you should have in your mind when you choose that new parameter. Okay? Okay, so I already mentioned kind of a few times here that there was this direct link between sort of how much bias current you got and how much transconductance you got, right? But really, there was sort of this degree of freedom that you had, which was changing that overdrive, which could actually give you more transconductance for the same unit current. So I'd actually claim that from a design standpoint, the so-called transconductance efficiency, or the GM divided by the ID, is probably something you're actually going to care quite a bit about, right? Because it basically tells you how much power do you actually need to spend in order to get a certain amount of GM, okay? So I will mention here this particular metric or figure of merit, this GM over ID, is a completely DC metric, right? It says absolutely nothing about the parasitics or the bandwidth or anything like that. This is purely just at DC, how much GM do you get per unit bias current. So we'll look shortly at kind of what are the implications of actually, including, let's say, the dynamics as well. But for now, let's even just focus on this particular parameter here. So I'm just showing you a plot now actually for a real device of if I change the gate to source voltage, what happens to this GM over ID metric, right? And so what you can see is as you decrease the gate to source voltage, this GM over ID metric kind of goes up, right? Which, based on our previous equation that we gave, kind of makes sense because we said that, if we said that GM is equal to 2 ID over VGS minus VT, if I just now pull that ID over and look at that as a metric by itself, it says that the metric should go as something like 2 over VOD or 2 over VD sat, right? So it makes sense that as you decrease that gate to source, of course that also decreases the VOD, your metric actually goes up. In other words, it improves. Now, there is one thing which you'll notice here is that, if this was really the equation for what should happen to that GM over ID, this should have kind of gone off to infinity, right? Like this should have just kept on increasing forever and over. Why does it not do that? What's happening? Yeah. Yeah, exactly. So once you actually enter the subthreshold region, then to zero order, the GM over ID becomes constant. Okay? And the reason for that is that, as we talked about a lot last time, when you get into subthreshold, the CMOS transistor actually kind of looks like a bipolar device, right? So in other words, when you get below that threshold voltage, the drain current versus gate to source voltage has an exponential relationship. And so just like we said before, let's say from a functional standpoint, GM is always just the derivative of the drain current with respect to the gate to source voltage. And nicely enough, if you have an exponential behavior there, then when you take the derivative, you just get back another exponential, just scaled by some factor, right? So in particular, and again, I hope all of you guys have seen this at least once or twice before. If you look at this, then that basically says that your GM is still just equal to that drain current divided by this new factor NKT over Q, which is typically referred to as the thermal voltage, right? So KT over Q, at least at room temperature, is something like 25 millivolts. As we said before, this N is typically about 1.3, something like that. So if you work that out, you'll see that indeed this peak number here, which is about 25 or so, makes a lot of sense, okay? Because it's really just being set by essentially the thermal voltage and that non-ideality factor from the capacitive coupling between the gate and the capacitive divider between the gate and the depletion region underneath, okay? Does this make sense to people, or? Okay, so let's again sort of take a look at this, metric as a design parameter. Okay. So again, if we're really looking at this GM over ID, we said that kind of if we had a long channel or a quadratic device, we know that we should be getting 2 ID over VD sat. Whereas if we had a bipolar junction or, in fact, a MOS transistor in the subthreshold region, we should have the sort of current divided by that thermal voltage. Okay? So, by the way, this relationship here is immediately sort of one of the main reasons that people say that bipolars are better than CMOS transistors. So just to be clear, what do people mean by that? What is it that's better about a bipolar versus a CMOS transistor? Yeah, for the same bias current, you get a higher GM, right? Because basically, you get that 1 over thermal voltage or that 1 over 25 millivolts. No matter what the bias current is, immediately you get that as the transconductance efficiency, right? Whereas with CMOS, the best we can do is basically knock, if we bring all the way down to the subthreshold region, we'll get close to that, 40 inverse volts of kind of efficiency, but actually because of that capacitive coupling or the capacitive divider, you actually don't get the full 40 inverse volts. Instead, you get something like 25, 26, something in that ballpark. Okay? Does this make sense to people, or? Okay, now one other thing that I should point out is I've shown here the curve for essentially the transconductance efficiency versus VGS for both the NMOS and for the PMOS. And hopefully you'll notice here that the two things actually look pretty darn similar, right? So maybe there's a slight shift in the curve, maybe the peak value is a little bit different, but overall the curves look very, very similar. So this implies that really, indeed, from the standpoint of this particular metric, then there's really not that much of a difference between NMOS and PMOS. So what is really the big difference between NMOS and PMOS that, at the end of the day, will actually affect you? Because it's clearly not from a DC, if current efficiency standpoint. Yeah, the speed is different, right? So in other words, even if I have the same transconductance efficiency, the parasitics I'm going to get, at least typically from the PMOS, are going to be worse than the parasitics I get from the NMOS. Now, by the way, I said typically because if you really go to some of the super modern advanced technologies, the way things are scaling are such that, or at least the way people are engineering the devices is such that the PMOS devices may soon actually be faster than the NMOS devices. That is largely surprising for people who have been doing this for a very long time, but nonetheless, that is the way things are going. So, in general, indeed, PMOS is slower than NMOS, but don't take that as a universal truth. Really, the more important point is that it's not typically the transconductance efficiency that's different between the two. It's really the sort of intrinsic speed you can get out of them that makes a much bigger difference. Okay? So, if you sort of look at this thing, I keep coming back to saying that I would like to use this as sort of in a design driven way. In other words, I'd actually like to use this GM over ID to figure out what are the real sort of if I give you some specs, how do I actually build a circuit that would meet those specs? And I will claim that this GM over ID is actually going to be a very good way to enable us to do that. So the reason I claim that is kind of a couple-fold. But really, the most important thing is that if I look at GM over ID as just as a parameter, I can always measure it, right? There's no reason why I can't measure that parameter either from SPICE or even from a sort of set of transistor IV characteristics somebody gave me, right? Because there's nothing sort of, let's say, arbitrary or poorly defined in this particular parameter, right? Once I measure the bias current, I can also measure the slope of the bias current in that region, and I immediately know both GM and ID. I can immediately calculate this efficiency parameter, okay? And I can do this completely independently of any short channel or other weird effects that may exist, right? Because once I have the IV characteristics, I'm done. I have everything that I possibly need, right? So that, as we'll see, and by the way, this is in contrast to, for example, if I tried to use VGS minus VTH. What's really painful about trying to use VGS minus VTH, especially if you don't know exactly what's happening inside of the device? Yeah, exactly. How the heck do you measure VTH? So does anybody know? How do you measure VTH? This is kind of a trick question, but go ahead.
Well, you can do some interpolation tricks where you get the parabola, and I know it's not a really well-defined thing, but...
No, okay, so what you said is exactly correct. You can say you can measure some IV characteristic and then try and interpolate versus some region that you assume you know what it looks like and look for the intercept. But physically, you don't know if that actually means anything or not, right? You don't actually know if the channel is actually inverted right at that voltage, or just it happened to be where you extrapolated. By the way, other people like to define threshold just as some magic current density number, right? So basically, the point there is that threshold really cannot be directly measured, right? You can come up with some ways of trying to measure it, but there's no real way of taking some arbitrary device and saying, oh yeah, this is really the threshold voltage, and now I know what the VGS minus VT actually is. Whereas with GM and ID, I don't really care what the device is. I can measure them, right? They're physically measurable quantities that I can immediately always get, okay? So as we'll see in 1 second, I claim that this is now going to be very useful to use as a sort of design-driven parameter. Now, the only thing that's a little bit annoying when you first look at that is that if you sort of think about the units of GM over ID, it's like 1 over volts. And I don't know. I mean, that's not so horrible, but I usually don't think in 1 over volts, at least not in my head, and I'm guessing you guys probably don't either. And it's not entirely clear sort of what the physical interpretation of 40 inverse volts or 20 inverse volts or 10 inverse volts of GM over ID would actually be. But nicely enough, there's a really simple way to just redefine things that hopefully will make it very, very clear exactly how you use this, okay? So the trick we're going to use is, rather than directly using GM over ID, I'm instead just going to define a new parameter, which I'm going to call V star, okay? So now here, if before all of the equations I showed you were sort of derived from some model, here there's absolutely no modeling involved whatsoever, okay? I'm just literally, by definition, going to say that V star is equal to 2 times ID divided by GM, okay? And again, there's absolutely no model involved there. This is simply by definition. Okay? So of course I can rearrange this, and this is where that original GM over ID parameter came into the picture. This is just to say that by definition, GM over ID is equal to 2 over V star. Okay? Or to say it another way, if I chose a V star of 200 millivolts, my GM over ID would be 10 inverse volts. Okay? So, why do you guys think I chose to define V star this particular way? What's kind of nice about this definition? Yeah, exactly. So, the whole reason I define things this way is because it's very reminiscent of the square law device, right? In other words, if I really had a square law device that was exactly following our sort of classic model, then you would have said that indeed the GM is just equal to 2ID over VGS minus VT, which in this case, that VGS minus VT would be exactly equal to V star, right? So the only reason I chose to define things this way was, again, because I'm kind of trying to make an analogy between VGS minus VT, or that overdrive voltage, and this V star. But notice the really big difference is that because this is by definition, I can always actually measure V star. Whereas VGS minus VT, I have no way of actually measuring, right? I don't actually know what that is because, again, I can't actually get at the threshold voltage, okay? So the point here is that you should remember the real devices we're working with are by no means whatsoever going to follow the square law model. It's just that we're going to use sort of this definition, which is really inspired by the square law model, to give us intuition into how we should pick this V star and how we should actually then, you'll see, use that V star in the first place. Okay? So just to make sure this is really very clear, I want to kind of recap a few of the things that we've said so far. Right? So if we think about the so-called overdrive voltage, or VGS minus VT, as we said several times now, the big problem with this is that I really have no way of measuring it. Right? And if I was to try and use a so-called VGS minus VT in any modern realistic device, the equations would just really quickly become totally horrible, right? Because there's all these effects that we talked about last time, velocity saturation, gate field mobility degradation, and so on and so forth, that would all, very quickly mess up the equations that you try to use to get any kind of reasonable intuition out of it, right? Now, the only good news is that indeed, if you had a long channel device, then that overdrive voltage would really tell you a lot, right? It would tell you how efficient you are in terms of getting a certain GM for a bias current. It would tell you what's the sort of drain to source voltage you need across the device in order to ensure it's in saturation, right? It would also tell you essentially, when is it that you're getting sort of a large RO versus a small RO, right? It tells you sort of how much relative capacitive parasitics you have, right? It has all these kind of nice physical links to what is going on in terms of the trade-offs that you're trying to make, right? So the trick here is that, as I said before, with V star, I'm just going to define it to be 2ID over GM. Okay? And again, the reason I'm doing it this way is because I can actually measure, or in fact simulate, all of those parameters very easily. Right? So there's no ambiguity whatsoever. You give me a transistor, you give me its IV characteristics, I can immediately tell you what is the V star at some given bias point. Right? So the trick here is that now, because I defined that V star to look sort of similar to that VOD, I can still try and make interpretations of what's going to happen to my transistor characteristics as a function of V star. In other words, I can say that indeed, if I reduce the V star, well, this is really by definition. If I reduce the V star, my GM over ID is going to get better, right? That's just by definition. But by intuition, I could say, well, if you reduce the V star, transistors are going to get slower, right? In other words, you're going to have more capacitive parasitics. Similarly, if I reduce the V star, then in general, the drain to source voltage you'd need to maintain a certain output resistance should also go down. Okay? But the key here is that when I made at least those last two statements, that's really sort of only an intuitive link. In other words, I can't say that exactly at a VDS of V star, that's exactly the boundary between saturation and triode, because it's not. Right? V star, again, is just something that I measured that's related to transconductance efficiency. It does not necessarily say anything about what the real quote-unquote VDSat actually is. Okay? So again, the only thing that is indeed precise with V star is that it's equal to 2ID over GM. Okay? And that's, again, simply by definition. So does this make sense to everybody? Or? Now, lest you think that this is just sort of some, esoteric thing that I just like to, define out of nowhere and have no idea of how to actually use this. What I want to do now is actually walk through a very simple example of designing an amplifier to show you exactly how V star is immediately very useful. Okay? So to keep life simple, let's just go with kind of like, a very simple conceptual amplifier. Okay? Very similar actually to the one I drew before. So let's say we have just some NMOS common source amplifier. I'm going to tell you it's driving some fixed capacitive load, and it has some bias current over here. Okay? So your job, of course, is going to be to pick that bias current such that you meet the overall amplifier specifications, but, have the minimum total amount of power consumption. Okay? So here's the specs that I'm going to give you that you have to choose, okay, or that you have to meet. So I'm going to tell you that your gain has to be, for example, greater than 4, okay? And I'm also going to tell you that your 3 dB bandwidth, for example, has to be greater than, I don't know, let's just make up a number, 250 megahertz times 2 pi, okay? Just, again, to make up a number. Okay, so now I'm also going to tell you that the load cap, in this case, is going to be 1 picofarad, okay? Now, finally, just to sort of show you how, once we've made this decision, life gets very easy, I'm going to tell you for now that we're going to use a V star of 200 millivolts. Okay? We're going to come back later and sort of discuss a little bit more detail how you'd actually choose that number. But really, it's coming down to those trade-offs that we discussed before of, you'd like it to be small to get good transconductance efficiency. But you can't make it too small because basically your transistors will have too much parasitics associated with them. Okay? So the first thing we need to sort of remember in order to use this is how GM is related to the gain bandwidth of our circuit. So you guys tell me, how is GM related to the gain bandwidth of a very simple amplifier like this? What is GM over CL? Yeah, so GM over CL, in terms of, let's say, the variables that I've defined here, what would GM over CL be equal to? I don't need the number, by the way. I just meant, I gave you a few parameters that I defined. Just, tell me what GM over CL is equal to in terms of these parameters. Yeah, exactly. Okay, now raise your hand if you, remember this or vaguely remember this or have seen this at least once or twice. Okay, good. So I don't think I need to rederive it, but if anybody would like me to, just let me know. But again, this of course comes about because the gain is just GM times R. The bandwidth is just 1 over R times C. So if you take the product of those two, you just get GM over C. Okay? Well, okay, so how did we say that what was going to be the relationship between GM and V star and the bias current? Just by definition. And you can flip back, 1 or 2 slides if you need to. There we go. So GM is just equal to 2IB over V star. Okay? So if I just combine those two things together, right, if I just push CL over here to the side, I can say that GM is equal to AV times the 3 dB bandwidth times the load capacitance. And then I can also say that that's equal to 2 times the bias current divided by V star. Okay? Now, notice, once I've done this, I claim, at least to 0 order in terms of the original problem I gave you, the amplifier is almost completely specified. Okay? With one small exception that we'll fix in 1 second. Because notice, once I've done this, I can now say that the bias current has to be equal to 1/2 times the gain times the bandwidth times the load capacitance times V star. right? If you guys remember, I said originally all you had to do was pick the bias current. Well, I'm done. There's nothing else I can do. This is the only bias current that will guarantee that I will meet my specs, at least with this V star. Does this make sense to everybody? Or? Okay, now, by the way, just, maybe to throw in some numbers, anybody happen to know what this turns out to be? How much bias current does this actually mean that you need? Ballpark, I don't need any I don't need the exact numbers. Close. Actually, I think you might be right. So basically, this is about, this right here is about a gigahertz. A gigahertz times a picofarad is something like about, 1e minus 3. This would divide that by 5. This multiplies it by 4. So, okay, yeah, it's about 800 microamps, something like that. Okay? So again, notice the power of this is that once you specified these things, you immediately know how much current this is supposed to take, right? No, no complicated, IV curve lookups or anything like that. You immediately know this is how much current this circuit is going to have to take, okay? Now, what is still missing in terms of you actually finally building this circuit? Yeah, so we haven't specified the sizing, and there's one other parameter that I never explicitly... The DC gate voltage. Okay, you're right. Although, actually, in fact, that's very much related to the sizing, as we'll see for both the sizing and the DC gate voltage. Once I've specified V star, both of those will pop out. Okay, and we'll see that a little bit later on. But there's one other thing that we didn't exactly explicitly take care of. You're right. Right now, I've done absolutely nothing about the parasitics from the transistor itself in terms of how they affect your performance. That is indeed an issue. We'll come back to that a little bit later on. But for now, let's assume that they're small enough that they don't have a big effect. There's one other sort of thing that I didn't exactly explicitly guarantee. You're right, although I didn't give the spec. So I suppose you're right. Swing was missing, but I didn't give a spec on swing. Okay. So you said that my output resistance is not infinite. So in particular, which sort of circuit level parameter is it that may not necessarily be met because of that? Channel length modulation. I mean, there's, let's say 3 specs here that I said that I wanted to meet. Which one of those 3 might I potentially not meet? Yeah, the gain, right? So the trick here is that so far everything we've said basically worked to ensure that I got a certain gain bandwidth, but I haven't yet exactly specified what the gain really would be, right? And of course, in order to do that, I need to figure out what the output resistance really will be and how that will vary as I change my sort of design parameters. Okay? Does this make sense to everybody? Or? So with that in mind, what I want to do now is spend a little bit of time talking about, indeed, how you would sort of go about doing your design to guarantee that you actually got the gain you wanted and not just the gain bandwidth. Yes?
So, I mean, I guess, why can you sort of turn that around and say, well, I haven't guaranteed my bandwidth necessarily?
Okay. So you asked, why can't I turn around and say that I may not have guaranteed the bandwidth? That's actually also true. So in other words, all I've really done in this procedure is I've guaranteed the gain bandwidth. But I haven't individually specified what either one of those two are. Right now, there's really only one free parameter there, right? Because once you fix the RO, that'll set both the gain and the actual bandwidth. That's a very good question. Okay, so with that in mind, let's indeed sort of take a look at the output resistance itself, but really more importantly, what it implies about the DC gain you can actually get. Okay, so this is really just kind of a reminder from last time. This is just showing you actually, it turns out not for our particular technology, but for some older technology, it's showing you a plot of what happens to the output resistance of some device in different corners as you basically sweep the VDS across that device. And as we said last time, kind of the meta point here was really that it's basically hopeless to try and model these things with something very simple like, that GDS is equal to lambda times ID, right? Because clearly there's all these sort of variations happening inside of there. And in particular, if I come up with some new weird-looking device, things may just look very, very different than what you'd expect to see from this very, very simple model. Okay? Now, having said that, the thing we really do need to keep in mind is that typically it's not really the value of RO, at least not most of the time, that you actually care about. usually it's actually the DC gain that you care about. Usually it's really that AV0 that at the end of the day is what you're trying, is the spec that you're trying to hit. Okay? So at the transistor level, at least, this AV0 is really kind of representing what's the maximum intrinsic gain you could get from the device itself. Okay? And again, I claim that actually that intrinsic gain is usually more important than intrinsically sort of what the RO itself really is. Because it's not that you really know, like, oh yeah, I need a mega ohm of output resistance. It's more typically that you say, well, I need a gain of 10, 20, 30, whatever that number actually is. Okay? So before we sort of dive into to sort of say what that's going to mean in terms of how we're going to do this, how we're going to use this in a design-driven way, I think it is worthwhile just mentioning a little bit sort of how you would actually do a simulation setup to characterize that intrinsic device gain. Okay, and in fact, I think this was a question that was asked on Piazza sometime maybe late last week or so. So what I'm showing you here is the circuit that I would typically use to actually characterize the intrinsic gain of the device. Okay? Now, I'll point out that this is actually done not just to sort of characterize it at one individual bias point. In other words, I'm not just, for example, going to diode connect that device. But what this actually allows me to do is change the drain to source voltage across that device and look at what happens to the intrinsic gain as you move that drain to source voltage around. Okay? So the way this works is as follows. I basically am going to bias my device with some given bias current, which, by the way, you're going to calculate exactly using the procedure that we calculated before, right? Meaning using the load cap, the gain bandwidth, and V star. And then what I'm going to do is I'm just placing this ideal amplifier in here so that I can change this VDS so that through the feedback, it'll basically control the drain to source voltage across the device. So notice, like you were asking before, I didn't do absolutely anything at all to specify what VGS is, right? Because I don't actually care, right? Because once I've specified this bias current, and I've specified the size of the transistor, to zero order, I'm also specifying essentially the V star. And so I'm just letting this amplifier basically decide what the VGS needs to be in order to actually get the VDS I wanted and this so-called current density, or essentially this bias current, given the size of the device that I'm using. Yes? Yeah. Okay, so the question was, it seems like, if this gate to source voltage is changing some, that will actually change the GM that you're getting. And you are, in many ways, let's say, correct, that, if I really measured the exact V star, it's probably going to change as you change the VDS. But it shouldn't change very much to the extent that basically the transistor is operating in a reasonable regime, right? So in other words, to say it another way, what I'm really truly fixing here is not necessarily the V star, but rather it's actually the bias current density. But at least once you fixed VDS, the bias current density, meaning how much current you had flowing per unit width of the transistor, is very closely related to the V star. In other words, especially if you fixed the VDS, then for a fixed VDS, there's a unique bias current density associated with each individual V star. And you're right, as you change the VDS, the V star or the bias current density would change somewhat. But again, this is to zero order going to tell us pretty darn close to exactly kind of what we really care about. Does that answer your question? Or? Okay, great. So now maybe I'll ask you guys a question. As I mentioned here, when I put this little op amp inside of there, let me get a pen that you can actually see. When I put that little op amp inside of there, I actually chose the gain to be only, quote unquote, about 100 or so. Whereas typically when you throw op amps around, at least when you do your sort of, let's say, basic EE40 or something like that, you typically like to think of op amps with infinite gain. Why do you think I did this? Why did I choose only a gain of about 100? Yeah?
You want to maybe avoid potential positive feedback effects.
Okay, you said I may want to avoid potential positive feedback effects. I think if I'm really using an ideal op amp, and as long as the transistor is not too weird, I probably don't have to worry too much about that. That is possible, but I think I don't have to worry too much about that.
You want like a little wiggle room for what the value of the gate voltage could be?
Okay, so you said I want a little bit of wiggle room for what the value of the gate voltage could be. That turns out to be exactly the reason, but now from a very practical standpoint, why? Why do I want to leave a little bit of wiggle room? let's see if we can get anybody else. If not, I'll come back to you. So why might leaving a little bit of wiggle room be a good thing? And this is, by the way, an extremely practical issue. Yeah. Yeah, exactly, just to save time, right? Because as an example, if I really said that AV is equal to infinity, what is SPICE or Spectre or whatever simulator it is going to try and do? Yeah, exactly. It's going to try and get that gate voltage exactly precisely correct to like some ridiculous number of significant figures, right? So in other words, you're going to launch this simulation, and for example, by the way, you should be using this circuit in your homework as well. You'd launch it, you'd be sweeping over like, I don't know, 20, 30, 40 different, bias points, and you'll just be sitting there, kind of twiddling your thumbs or playing video games or whatever it is you do while you wait for simulations to run, because it'll just be trying to calculate, down to picovolts exactly what that gate voltage is supposed to be. Okay, so the real point there is that you want to choose the gain in that op-amp high enough that you're confident in the accuracy of your results, but not so ridiculously high that you're just sitting there waiting for the simulation to calculate a bunch of, or try to calculate things well beyond the precision you actually care about them. Okay? Does this make sense to everybody? Or? Okay, so once you use that circuit, what you're going to get back is kind of a plot that looks something like this, right? So again, perhaps what's perhaps not too surprising is that as you sweep that VDS, there's a really sort of strong trade-off between what the actual VDS really is and how much intrinsic gain you can actually guarantee out of the device. Okay? So just as an example, you can see that as long as I, for example, let's say have more than, I don't know what this is, 0.3-ish volts or so, then for this 0.18 micron device, at least at the given V star that I was using or the given bias current I was using, I could get maybe a gain of more than about 20 or so, right? But I also have to be careful that if the voltage got too large, then again, my gain might actually roll back off because of that substrate current body effect that we talked about last time. So it turns out the way we're really going to use these plots is actually, again, very much practically driven from what we care about in our amplifier design. So in your amplifier design, what is it that you think you might care about from a sort of specification standpoint? What is it you think you might want to be able to guarantee? Say that again? You said something about in the middle, but let's say more generically. Forget anything about this plot. What,
Oh, so do you mean like over the process variation?
Oh, I'm not worried about process variation for now. I'm saying, I know nothing about analog design, but I want to somehow spec an amplifier. So one of the specs we already mentioned was that we wanted to guarantee a certain amount of gain, right? What's another sort of, that based on this plot now, what's another related thing you probably have to specify in order to ensure you really can meet that specification? Yeah? Yeah, okay. You said the output swing, right? And that's exactly actually correct, right? So if somebody comes to me and says, you know what? My amplifier needs to have an output swing of somewhere between, I don't know what this is, let's say 0.4 volts, and I don't know, let's make it up 1.3 volts or whatever that number happens to be, right? So once you get that spec, you'd basically you'd take this plot. By the way, you should have a whole bunch of these plots for like different V stars, different channel lengths, and so on and so forth. You then say, okay, fine. So if that's my spec on the swing I can get, or the swing that I should be able to support, then now I just have to check what is the worst case gain I can actually guarantee under that given swing, right? So in this particular example, it would be that you'd be limited on this side of the picture, and you'd say you could get a gain of whatever that is, 22, 23, something like that, right? So now, of course, if somebody says, well, okay, no, you know what? I don't actually need that swing. Instead, I'm actually only okay with, let's say, 0.6 to, I don't know, 1 volt. Then now you could say, okay, well, given this channel length of the device, now I can actually guarantee a gain of 20, whatever, 25, 26, something like that. Okay? So in other words, the real way you're going to use this is you're basically going to say, look, I have this collection of these plots that tell me what the intrinsic gain of the device is as a function of V star and as a function of the channel length, right? And of course, each of the plots is telling you what happens to sweep VDS. So from a design standpoint, the way you should really use this is you basically say, well, once I know what my swing is supposed to be, in other words, what the voltage range needs to be, I should basically just go and pick a device that ensures I get more than the gain I was targeting over that voltage swing range, right? So in other words, if I said I need a gain of at least 20 over, this, let's say, whatever, 0.4 to 1.3 or something, I'd go and I'd look through all these different plots, and I would find all of the plots that give me at least this gain over that range. Now, by the way, that would still result in hopefully a number of different possible devices and different bias points that would work. Which then particular set of devices do you think you would choose? Or which individual device, I guess I should say, would you actually choose?
Smallest.
The smallest. Smallest in what respect?
Area.
Okay, well, so there's width and there's length, yeah? Parasitics. Okay, so that's you guys are kind of saying the same thing, but let's maybe split it in two ways, right? So there's channel length that you might be able to play with, and there's basically V star that you might be able to play with. So which of the two do you think you might want to, and each of those two vectors? Let's maybe do channel length first. So which channel length would you want to choose? Yeah, the smallest channel length you can get, right? Because once you know you can meet the gain, why would you go any longer channel length, right? Longer channel length only gives you more parasitics, makes the devices larger, everything just gets worse, right? Okay, now how about for V star? That one's a little bit more of a trick question, by the way.
You picked that, right?
All right, well, okay, yes. Typically, I already picked that ahead of time. Okay, and by the way, as we'll see later, the way I typically picked that ahead of time was indeed by deciding, well, I kind of know roughly what speed my circuit is supposed to be operating at. Based upon that, I can probably actually come up with a pretty good guess what the V star needs to be. Okay? So in other words, once you've picked the V star, really, you're just going to pick the shortest channel length you can that meets your gain over swing specifications. Okay? Does that make sense to everybody? Or? Okay, so now, as we kind of already hinted at, and as I'm sure you guys have already seen from, let's say, EE140, right? Obviously, there's going to be conditions where your minimum channel device simply does not have enough gain over the voltage swing that you were interested in, right? And so then what you will indeed do is you'll basically choose a longer channel device, right? And of course, the only reason longer channel helps is because it helps to basically mitigate some of those, let's say, drain-induced barrier lowering and channel length modulation and those other effects that we had mentioned were causing the output impedance of the device, okay? So this would be, for example, another plot that, again, it's just showing that over the same voltage swing range, indeed, potentially you could get a higher intrinsic gain out of the device. And once again, the whole trick here is that you're just going to choose whatever the shortest device is that actually meets your specification. Now, having said that, just before we sort of move on, can anybody else think of another way of actually getting more gain out of a device rather than just increasing the channel length? Okay, use more than one device? How? There we go, Cascode, right? So hopefully you guys spent a lot of time talking about this, for example, in 140, perhaps even in 105, right? One very standard way of increasing the GMRO, or really the AV0 that you can get, is basically to just use a Cascode device. Okay, so let's say that it would look something like this, where that VB is just some fixed bias voltage. So if your original device gave you an AV0 of gain, roughly speaking, what would the Cascode give you? Yeah, basically, roughly speaking, it gives you something like AV0 squared. Okay? Now, obviously, the penalty is that you probably need more drain to source voltage to actually get that full AV0 squared. But as we'll see probably in about a week or so, it turns out that actually in most cases, in many cases of practical interest, even for the same sort of VDS constraint, if you really are sort of limited by the gain you can get, it's pretty common that using a Cascode will actually be better than just moving to a long channel device. Okay, we'll see that in a lot more detail later on, but yeah.
And the previous slide where you have the AV0 versus VDS plot, you were sort of saying when you're looking at the resistor plot, like you don't really want to couple the model because it's complicated with this model. I mean, this seems very similar in a lot of ways. Like, I wouldn't sort of necessarily, I think, intuitively know that the curve would sort of look like this. So, I mean, I guess you're using like Spice kind of as a workup table for this. Is there a way that you would get
Okay. So just to maybe summarize the question for the camera and for everybody else, the question was basically saying that, hey, look, there still isn't really a model per se for the RO here. We're really just kind of using SPICE as a lookup table, right? So is that sort of, let's say, maybe, how should I say this? I guess what you're asking is there any intuition that we can use to really tell us that, yeah, the results we're getting from this lookup table kind of make sense? I think that's maybe the way to rephrase the question. That's a very good question. That is indeed exactly why we spent some time talking about kind of what the physical effects really are, right? Because what you should expect to see is, the exact numbers are kind of usually difficult to get right. What you should expect to see is that indeed, if you kind of know roughly where the junction breakdown should be, that's kind of around where things should start rolling back off, right? Similarly, if you know sort of, you should be able to see that as you change the V star, or equivalently change the quote-unquote VD-SAT, you should be able to see that where it sort of starts to flatten out like this also is moving around with that biasing that you're doing. So unfortunately, the answer is that getting it exactly right is pretty tough. And in fact, even getting the model exactly right is pretty tough. But as with anything else, you should be using this essentially not to say that I know my gain is going to be exactly X, Y, Z. It's just to say, look, as long as I do this and I leave myself kind of a good margin, meaning I check all the different corners, I check all the different bias conditions, then as long as my model is reasonable, I can get a pretty reasonable confidence that it'll actually meet the specification I'm interested in. Does that answer the question? Or? It's a very good question. Okay, great. So any more questions on this? Or? Okay, so just a couple of sort of side notes, just sort of out of interest. One of the most classic complaints that you'll get from any sort of old, crusty analog kind of person, perhaps even new, not so crusty analog people as well, is that if you start scaling into these newer and newer technologies, typically the maximum output, the maximum intrinsic gain you can get, in other words, the maximum AV0, tends to go down. Okay? So you can kind of see that simply on this plot by just, in 0.5 micron, maybe I was able to get like, 75. In 0.25, now I was only able to get like 40. 0.18, it was only, a little bit less than 30, and so on and so forth. And in fact, these days, if you go to like, a 45-ish nanometer or 30 nanometer transistor, this number is probably somewhere down in the range of 5, 6, 7 tops. Okay? So again, one of the sort of biggest complaints you'll probably hear from people is, oh, darn it, I don't want to work with these short channel devices because, the gain I can get is just horribly bad. Okay? Well, there is some truth to that, but we need to be a little bit careful because remember, it's not that you're really always going to be putting, these huge drain to source voltages across the device, right? So in other words, you're typically going to be constrained in sort of how much drain to source voltage you actually have across the device, simply because you want to use it to get a reasonably large output swing. And so the kind of good news there is that if you really zoom in on the regions where the drain to source voltage is reasonably well constrained, meaning it's kind of close to whatever that minimum value you'd like to use really is, now actually the picture doesn't look quite as bad. In other words, the actual gain you can get from a short channel device versus the longer channel devices doesn't tend to degrade quite as badly once you really constrain it to this more reasonable VDS range. Does this make sense to people? Or? So this is kind of, by the way, like silver lining saying that, yeah, things are getting worse, but maybe not quite as quickly as people like to complain about. Okay, so with that, let's maybe just kind of quickly walk through a more complete design example. Okay, because now we really know sort of not just how to get that bias current right, but we actually also know how to basically get the gain and therefore the bandwidth right as well. So again, I'm just going to come up with some arbitrary specifications here. So I'm going to say the gain is greater than 70, bandwidth is 100 megahertz, and the load cap is 5 picofarads. Okay? So it turns out the very first step in my design procedure is just going to be to say, okay, well, if I need a gain greater than 70, I go and I take all those plots that I did for my particular technology. And here I didn't explicitly specify it, but there would also presumably be some voltage output range or voltage swing at the output that I would like to guarantee. And to do that, I would say, okay, in order to get this gain of 70, I need a channel length of 0.35 microns. Okay? Once I've chosen that channel length, then, in fact, actually even before I've chosen that channel length, I also immediately know, just based upon the frequency and the load cap, how much GM I need. Right? Because again, GM over C is always the gain bandwidth. And so I immediately know I need 3.14 millisiemens of GM. So now, if I then in this case, it's going to be somewhat arbitrary. But again, let me just pick a V star of 200 millivolts, because I know that for roughly this frequency range, that's kind of a good choice to use. Then again, I immediately also know what the bias current actually is. Okay? Because if I know that I needed 3.14 millisiemens with a V star of 200 millivolts, that immediately tells me I need 314 microamps of bias current. Okay? By the way, this V star of 200 millivolts happens to be a kind of convenient number because there's an exactly factor of 10 between the bias current and the GM. Okay? So just keep that in mind because it'll allow you to do the calculations, very quickly in your head. Okay, so this is all fairly similar to what we said before. Here's where we really sort of complete the rest of the procedure. Okay? So as we said, we picked the L based upon that gain constraint. We picked the V star for now. Let's just assume it's somewhat arbitrarily, but we'll say in a second more sort of how you do that intelligently. We determined the GM. We determined the bias current. So now all we actually have to do is figure out what is the actual size of the device. What is the actual WNL so that either you or the layout designer can go and literally enter this in, on Cadence or whatever your layout system happens to be. Okay? So here's again where we're actually just going to use SPICE as a lookup table, right? Because as we said before, once we fix the V star and at least have a reasonable range for the VDS, then now actually we know exactly what the bias current for the device is for a given size of transistor. Okay? So just as an example, I could take a 10 micron wide transistor by 0.35 microns long. And I could take all my lookup tables and just sweep that V star. And what it would tell me is that if I wanted a V star of 200 millivolts, as an example, this 10 micron wide device would have 141 microamps of current flowing through it. Okay? Well, so that says that if I know that that's the case, and I also know that at the end of the day what I actually want is 314 microamps, then really all I have to do is figure out how much, what's the scale factor relative to that 10 micron device that I should use to get the final bias current I want. Right? So this is exactly how I would calculate. In this case, that I wanted 22 microns. Because it would just say, if a 10 micron device is 141 microamps, but I actually want 314 microamps, I just divide these two and immediately figure out I need a 22 micron wide device. Okay? So in other words, I'm again just using essentially SPICE as a lookup table to tell me for a given V star, what is the current density of the device? And once I know that current density, if you tell me how much current you want, calculating the size is trivial. Does this make sense to everybody? Or? By the way, just to make sure it's sort of clear, people will sometimes refer to this kind of methodology as a so-called constant current density methodology. What they really mean by that is that, again, you choose a V star that sets the current density, and therefore all of the design simply involves scaling off of, or choosing an exact device width based off of a known current density. Okay? So again, in order to actually do real designs, you're going to have to create these plots for, lots of different types of devices, lots of different channel lengths, and so on and so forth. But I guess the good and the bad news is that's exactly why you had this as problem number 3 in your homework, so that you'll be able to use these moving forward when you do designs in this particular technology. Okay, so, yes, question.
Are you going to get back to the schematic or not?
Oh, to the picture I was showing before? Yeah, so there are some details in that schematic that I was skipping over for now, but if you have questions, go for it.
How do you actually set the V star with this?
Okay, so the question was, how do you actually set the V star with this? So the way it's actually done is very similar to what we did in that earlier picture, where I was showing you how to actually sort of measure the AV0 as a function of VDS. So everything that's over here on the left is really just sort of a copy of this circuit, with its only intention being to figure out what the VGS actually needs to be. Okay? So if you remember, I said that basically once you pick the V star, that's also sort of implicitly setting the current density. So indeed, what I'm basically doing is I'm saying, well, okay, I know how much bias current I need, so I'm going to feed that in to the drain of this transistor here. And okay, I don't really know exactly what the VGS is supposed to be, but so I'm just going to use that same op-amp trick to fix the VGS based on the nominal VDS that I want to support. And then I'm just going to take that and use it really as a bias for the real amplifier that I'm going to measure. And then the only additional trick I played here was I added this little voltage source in. That's kind of like the small signal voltage source. In other words, that's the real small signal analog input off of this nominal bias.
Yeah, so I guess the thing I missed also in
Okay. So the question was, basically, is there, where's the VDS really getting fixed? And indeed, this would be something you'd kind of have to pick based on, I want the nominal VDS to be some value, and then I do my design kind of either off of that nominal VDS, or I may just sort of sweep it across that range, again, to check that my gain is met across the range of VDS I'm trying to support. But typically what you'd do is you'd basically say, well, if there's a certain swing range I want to get, you'd pick this VDS such that you're sitting in the middle of that swing at the nominal bias, right? Or somewhere close to that middle. And then you'd do all the design based on that, and you'd come back and just double check that indeed, as you sweep that VDS around, you're still actually meeting all the specifications that you wanted. It's a very good question. Yes?
The op-amp that's used there, it has like a really high output impedance, right?
Oh, actually, this one really is an op-amp, so it has 0 output impedance. As we'll talk.
Then how do you like put in the small signal voltage? Like, because normally you put like a capacitor.
Oh, so you notice how I put the voltage source in series with the op-amp? So in other words, that voltage source is just being added to the output of the op-amp. Like, I'm not modulating this whatsoever. I'm just changing this voltage relative to that point.
But like, how would you do it in real life? Like,
Oh, I see. You're asking how do you do this in real life. Okay, very good question, yes. In real life, there's probably some sort of AC coupling capacitor, or in fact, what you'll much more commonly do is if you have a differential pair kind of amplifier, the tail current source would actually set what this quote-unquote nominal bias would be doing. It's a very good question. Here, this is obviously just by simulation, and this is for me to sort of figure out what that bias needs to be. In real life, you'd probably do some sort of tail current source or a current mirror and AC couple into it to get this about right. That's a very good question. Other questions on this? Or? Okay. So just to sort of show that indeed this is a useful thing to do, I'm just showing you here that indeed once I followed this methodology, for all intents and purposes, I got my design pretty much dead on. Okay, so I just literally followed exactly the procedure I mentioned, and now I'm just showing you what are the simulation results. And they're basically just saying, indeed, I'm getting exactly the specs that I was predicting that I wanted. The point of showing you this is not to say that, to rub myself on the back and say, oh yeah, I'm really good. It's to say this actually does work. Okay? And the reason it works is because, again, we chose all the parameters we were dealing with in a way so that any uncertainty about what the device model really is was taken care of by essentially just using SPICE as a lookup table, right? Because again, I knew exactly what the GM I needed was. I knew basically what gain I wanted to hit. So then I just used SPICE as a lookup table to figure out the mapping between those GMs and those gains and et cetera to what the actual device width and length really need to be. Okay? Now, the question that, of course, we kept coming back to was, how in the hell did I pick this V star of 200 millivolts? Why didn't I pick 75 or 50 or 100 or anything like that? Well, to really answer that, we have to look at the AC model. Okay? So let's just sort of look now more carefully at the sort of AC performance of the devices and, of course, the small signal model for the transistors from an AC standpoint. Now, again, the good news here is that in many ways, things don't really change very much here, no matter kind of what type of transistor it is that you're really looking at. In terms of the actual sort of, let's say, capacitors you need to add in, things are always kind of basically the same. So if I take, let's say, an NMOS transistor in this particular case, what are kind of the capacitors that I need to add in to actually get my complete small signal AC model? Say that again? Gate to drain. Okay, you said that there's a CGD. That's indeed correct. What else? CGS. Okay, good. Anything else? There we go. There's actually a CGB. There's a gate-to-body capacitor. Okay, so by the way, these are usually referred to as the intrinsic capacitors. Okay, and they're called intrinsic because basically they're sort of fundamental to the way that the MOSFET operates. In other words, it's an MOS transistor. There has to be some capacitance from the gate to the drain, gate to the body, gate to the source. Okay? What other capacitors do we need? Yeah, okay, so there's a drain to body junction capacitor. Anything else? Yeah, of course, say source to body CSB. Okay? And so, by the way, these are so-called extrinsic capacitors because these, unlike the other case, they're sort of, they're there, they exist, but one could argue that, fundamentally they don't have to be part of how the transistor operates. They are indeed there, there's kind of no real way to get rid of them, but they're not, intrinsic to the operation of the transistor. Okay? Does this make sense? Or? So in other words, if it's a transistor, it's an MOS, right? So an MOS is indeed a capacitor, right? So in other words, the CGD and the CGS, they're directly related to the fact that it is an MOS transistor. Whereas those other capacitors, it could be some other kind of transistor or just basically any other thing, and they exist because of the way we happen to be building it, not because of intrinsically they have to be there to get a transistor to work. Okay, great. That's really more of a naming thing, just because you may hear intrinsic versus extrinsics. Practically speaking, it doesn't matter too much. Okay, so similarly, we can do a small signal model for the PMOS. And here, hopefully, things are not very surprising in that, of course, if we looked at the intrinsics that we talked about before, all of those, of course, also have to be there, right? So we have gate to source, gate to drain, gate to body. We're, of course, also going to have those same junction parasitics from the source and from the drain. What's the only other thing that's kind of missing from this particular picture that, for better or for worse, is often not necessarily captured in your SPICE model? What else is missing here? And this is, again, a PMOS transistor. Say that again? Yeah, exactly, right? So there's an N-well right here. There's a P substrate right there. So as usual, we've got a diode, which means we need yet another capacitor here. So that would be something like C body to substrate would be an additional capacitor that should actually exist in this small signal model. Now, hopefully the body is sort of strongly tied to one of the supply rails or something like that, so you don't have to worry about this too much. But again, user beware, because if you're doing something where it really matters, this could indeed actually have an effect. Okay? Okay, so just one, let's maybe final thing before we wrap up for today. That small signal model, again, I think all of you guys have seen many, many times before. But if you really actually went and sort of looked at either SPICE or Spectre's output, you may have noticed something that was actually a little bit strange. So how many of you guys have actually done like a .op or a .ac and opened literally the text file that was got spat out to you from either SPICE or Spectre and looked at all the different parameters it was listing for you? Anybody done that? Wow, only a couple of brave souls actually looked at the text output. Like you guys just love the GUI or something, I guess. I don't know.
You mean like look at all the parameters or look at all the parameters that are there?
So what I mean is, you took a transistor, you biased it up, and then you looked at, it would typically say something like GM is this, RO is that, or maybe GDS is that. And then it would usually say something like CGS is equal to something. And then interestingly enough, it would also say CSG is equal to something. So anybody ever wonder why the heck is it giving you both CGS and CSG? By the way, who's actually seen that? Okay, a few of you guys. So I strongly encourage you go run, do this exact experiment. You'll see there's probably way more capacitor entries in that table than you may have first expected. So the reason for that is actually fairly interesting. And to understand why, we need to kind of give ourselves a little bit of a reminder as to what capacitance is in the first place. So let me ask you guys, how is capacitance defined? Yes, but okay, so how is it defined? Okay, it is indeed from the charge you store, but let's say like the Physics 101 or Physics 7a or whatever it's called here. What's like the first thing that they usually tell you is the definition of a capacitor? Yeah, they usually say that Q is equal to CV. Okay? So it turns out they were lying, but they were doing it to be nice to you. Right? In reality, the definition of capacitance is actually that the capacitance is equal to the change in charge with voltage. Okay? And by the way, when you specify the change in charge, they even mean the change in charge at a particular node relative to the change in voltage. Okay? So if you think really carefully about a MOSFET, there's 4 independent terminals, right? There's a source, a gate, a drain, and a body. So from the standpoint of voltage, that means there's 3 independent voltages you can define. Because remember, voltages are always relative, right? So there's 3 independent voltages that you can define between those 4 terminals. Similarly, there's actually 4 charges on that MOSFET. Okay? There's charge at the source, charge at the drain, charge at the body, charge at the gate. Now, the only thing that sort of has to be true about the charge in the MOSFET is that all of the charges added together have to sum up to 0. Okay? So in other words, it means that there's kind of 3 independent free variables here. Right? You can actually specify 3 of those charges without saying anything about what that 4th one actually has to be. Okay? So if I have 3 independent charges and 3 independent voltages, how many different combinations of capacitors are there? Yeah, indeed, 9. You know, you guys can at least read. That's certainly true. But it's just 3 times 3, right? Because each independent charge can be changed by each of the 3 independent voltages. Okay? So just from a sort of notation standpoint, this is why SPICE actually gives you all of those different capacitor numbers. It actually should give you 9 different capacitors. Because it turns out that each of those is physically a distinct capacitor. So in other words, if I say that I have a CSG, what that actually means is it's the change in charge at the gate due to a change in voltage, change in charge at the source due to a change in voltage at the gate. And for better or for worse, that may or may not be the same as the change in charge at the gate due to the change in voltage at the source. Okay? So in particular, if you looked at, for example, CGD versus CDG, you'll typically see that they're different. Okay? Because, for example, changing the voltage at the gate certainly changes the charge in the channel, which changes the charge at the sort of drain side of it. Whereas changing the voltage at the drain may not directly influence the charge at the gate. Okay? And so again, you'll actually see these things where you'll see like, one of them might even be negative or 0 and things like that. It's, nothing is wrong. It is indeed just SPICE being very meticulous about how capacitance is actually defined. Okay? Does this make sense to everybody, or? Yes?
I mean, not physically, like what's going on? Is there some frigid field effect that happens inside the device, or?
So you mean, so the question was, do you mean physically what's happening with that example that I just gave in terms of gate to drain versus drain to gate? Yeah, so what's physically happening there is that if you change the gate voltage, that will mirror some charge in the channel, right? And usually we'll assign some percentage of that charge either to the drain side or to the source side, right? However, if we change the voltage at the drain to 0 order at least, that doesn't have a big impact on the charge that's actually seen on the gate side. And so because of that, there's an asymmetry there. That's why, indeed, CGD may actually be very different than CDG. Is that clear? Or? Okay, great. More questions on this? Or? Okay, so we'll wrap up next time with kind of completing all the stuff on the sort of transient performance and kind of wrapping up